So everyone got their test back. Everyone who's here. I think the mean was about a 75 or 6 with the curve. I'm going to do a little bit of review from last time because it is a long time ago, a week ago. And then we're going to launch into chemical reactions today. Okay, so let's just do some review. I want to talk a little bit about acids. So are acids molecular compounds or ionic compounds? No one wants to answer that? They're molecular compounds, right? But they are very special molecular compounds. They are molecular compounds that release ions when they hit water, right? So when they dissolve in water, right? So they are molecular compounds that release ions in water. And in particular, one thing is always an ion that's released. H plus is always one of these ions. And then there's some other ion, okay? So for example, we have the strong acid, hydrochloric acid, okay? You put HCl in water, and it breaks into ions, which we would then write aqueous, because what does aqueous mean? Dissolved in water. Exactly, dissolved in water. So HCl is an example of a strong acid. There are 6 strong acids. Okay, if you look on, actually, it's like, where is it? I think it's in the handout, that the previous packet. Previous packet was part 1 of chapter 4. This is part 2. In the previous packet, you have a table of acids. Am I right? Does anyone have that with them? I'm sure it's there. Maybe not. I don't know. Yeah, the previous packet. Yeah, that's it. Does that, the first page, is it a table of acids? Oh, where the heck is the acid table? I must have given it out.
Yeah.
Oh, it's on the back page of the previous packet? No, that's just, you're thinking of the solubility table.
Here. It's on one.
You're right, yeah, the back page of the previous packet. So the 6 strong acids that are given on this is the back page of, it's also posted on Blackboard, of the handout for chapter 4, part 1. This guy here that says chemical reactions is really the handout for part 4, chapter 4, part 2. Okay, so anyways, there are 6 strong acids, which I told you about: HCl, HNO3, HBr, HI, HClO4, and H2SO4. There are only 6 of them, but you need to memorize them. Okay, I'm telling you now, you have to memorize these acids. That way you'll know that they're the strong acids. There are many, many acids that are not strong. We'll talk about those in a minute. But anyway, every one of these strong acids breaks into ions in water. So we say they are aqueous. These ions are aqueous, they're dissolved in water. We also say, so this whole process here of taking an acid, and the fact that when you put it in water, it ionizes, we say that strong acids completely ionize. They completely form these ions in water. So the strong acids, we have different terminology for this. We say completely ionize, meaning form ions in water. But we also could say they completely dissociate in water. Okay. Now, we also have weak acids. And while there are only 6 strong acids, there are literally thousands of weak acids. And if you want to talk, just go in the hallway. I don't mind, but don't talk in class, okay? All right. So weak acids are also molecular compounds. They release hydrogen ions in solution, but they do not release nearly as many. Only a little ionization happens. So they're molecular compounds that release H plus in solution, but not much. Very little H plus is released. But still, they do release some, and they are called weak acids. So for example, we have acetic acid. I believe that you're doing a vinegar lab today. Is that true? Oh, next week then. All right, so next week you're doing the vinegar lab. Vinegar is a solution of acetic acid. So you're going to be doing a titration of acetic acid in that lab. And acetic acid, HC2H3O2. You can recognize here that this C2H3O, well, what happens is you get a little bit of release of H plus. So notice I drew a small arrow going forward. This only happens a little, and a big arrow going back. You'll learn a lot more about this. You'll learn a lot more about this in Chem 104, where we study equilibrium. But for now, let's just say that a little bit of H plus is released. And the other ion, does anybody recognize what this ion is from the polyatomic ion chart? See, back in the day, we had to memorize these, but now you can look them up. But look it up. It's acetate. It's acetate on, which makes sense because it's coming from acetic acid. And you could see this is the acetate part there, and this is the H that gets released. So we say that this first H here is the acidic hydrogen. That's the hydrogen that gets released. That gives you what you have on the right of this form of this reaction. Okay, so we often write this acid as HOAC, and in fact, I think that's the way it's written up in the lab. I'm not sure, but I think so. And OAC is just an abbreviation, OAC minus, for the acetate ion. So again, this is just the same equation. It's just sometimes you'll see HOAC, sometimes you'll see HC2H3O2. Yes. Can release H plus onto? No. But water is the only solvent that we talk about this semester, and that's why it's so important, because we're always putting acids in water. Okay, but next semester you'll see that there are many reactions of acids, and water is a very interesting compound, but I don't really want to talk about that because it's beyond our scope. But yeah, sure, there are other things that weak acids release H plus to. Okay, so we're going to study some acid reactions soon. I just wanted to go over that because I don't know how many people were here last time. And I also want to talk, since we spend a lot of time on reactions in solution, I'd like to talk about what happens when different substances come in contact with water. Okay. So let me just write, when different substances are put in water, what happens? We know what happens to acids, but what about other compounds? Okay, so the question is, do they dissolve? in which case they would be, if yes, then we say that they are soluble. And we say that a solution forms. If no, then they are insoluble. This is just some vocabulary that I talked about last time. And they basically sit on the bottom. So when you take a solid or a liquid, or even a gas, a gas isn't going to sit on the bottom. And a liquid is going to sit wherever the density tells it to. But if you take a solid and you put it in water, it could dissolve and be a nice homogeneous solution, or it could end up pretty much just sitting on the bottom. And we need to know what happens. And last time I showed you a solubility chart, which is good to look at for ionic compounds. So let's break this down into ionic and molecular compounds. So for ionic compounds, you really can't tell. You just can't tell very easily whether it's going to be soluble or not. So I'll just write, you can't tell easily. So we use this solubility chart, which my pen isn't working, so I'm standing here looking stupid. So I actually showed you this solubility chart last time, and we talked about whether how to use it. Okay, so this is for ionic compounds only. Okay, and just throw an example out. What about barium nitrate? Let me show you the whole thing. So suppose we have BaNO3 2. Is it soluble or insoluble? So what this table is broken down into two sections: ions that are generally soluble and ions that are generally insoluble. Okay, so if you look on this chart, you see that nitrate is over here, and nitrate is in this compound. So barium nitrate is a nitrate. Nitrates are generally soluble, and there are no exceptions. So this guy is going to be soluble. Okay. Another example would be, and I'm not going to do them all because I did them last time, but what about silver chloride? Soluble or insoluble? Insoluble. Now, which rule did you use here? It's an exception to the generally, chlorides are generally soluble, but not when paired with silver ion. So this would be insoluble. Okay, let's try sodium phosphate. Yeah, you could either use this rule here. Compounds with sodium are generally soluble with no exceptions, or you could go down here and see that phosphates are generally insoluble, but not when paired with sodium. So it's you have to learn how to use this table. This table is really your friend. Please use it. So that's how you tell if a ionic compound is soluble or not. You have to use the chart. So what about molecular compounds? Okay. At this stage of the game, you have to be told if a molecular compound is soluble, because you really don't have the chemistry knowledge to figure that out. That's a giant topic. Well, it's a unit anyway in Chem 104. Okay, so right now you need to be told. It has to do with the attractions of that molecule to water and the attractions of the molecules to each other in the compound. And that's a big unit, like I said, in Chem 104. So right now you need to be told, and I'm telling you that acids are generally soluble. I don't know of any exceptions that you'll come across this semester. So when you see an acid, you could write AQ. Okay, that's what you write next to something that's soluble. All right. So the next question kind of becomes, what's present in solution when a molecular compound dissolves? And what's present in solution when an ionic compound dissolves? So what's present in solution when an ionic compound dissolves? So what's the answer to that question? Well, an ionic compound doesn't have H plus. It'll have like sodium chloride or, potassium phosphate or something. But when you take, say, KCl, you have solid KCl and you put it in water, okay, you get these aqueous ions. It breaks into ions, okay? If you put sodium sulfate solid into water, you'd get sodium ions, and you would get 2 of them for every formula unit of sodium sulfate and sulfate ions. Okay. Now, if you put an insoluble compound in water, you're not going to get any ions. It's going to sit on the bottom, right? These are soluble ionic compounds. For an insoluble ionic compound, and you put it in water, it basically just sits on the bottom, mostly. Okay. So now, what happens when you dissolve a molecular compound in water? Here, so this is now when a molecular compound dissolves. What's present in solution? So let's take a molecular compound, ethanol, has a formula C2H6O, okay? And you put that in water, it's a liquid, put it in water, smells like vodka. And you just don't change, it still stays molecules. But we say aqueous, so now it's dissolved in water. But it's still the same molecule. Okay, it doesn't produce any ions, it's just dissolved molecules, yeah. Because they're acids. That's why they release H plus. They're very special. They have what we call an acidic hydrogen that is releasable as a proton. It's just because their attraction to the rest of the molecule is just different. Okay, so when a molecular compound dissolves, what's present in solution most of the time, you bring up a good point, which I was going to go over next. So most of the time, they stay as molecules. So what is the big exception here? Exception is, of course, acids, because we know when acids are molecular compounds, but they're unique. So when you put them in water, they break into ions. Acids are, as I've already said, molecular compounds that break into ions in solution. and H plus is one of them always. Okay, so for example, HClO4, you put it in water, you get H plus and ClO4 minus. Okay, so what about weak acids? When you put weak acids in solution, they produce some ions, but much less than strong acids. Okay, so now I want to talk about a property of solutions of soluble ionic compounds and acids, okay? And it turns out that these compounds, you put them in solution, that solution conducts electricity, okay? So solutions of acids and soluble ionic compounds can conduct electricity. So I'm going to show you a very sort of crude apparatus that you could use to figure this out. I used to do a demo of this, but it turned out that I was actually very dangerous, so they made me stop. Oh, well, anyway, I can't do any demos in this room because we're not in the same building as all the materials. In fact, I don't even know where all those materials are anymore because they are scattered all over the building too. But anyway, all right, so let me show you this apparatus. This apparatus is how you could tell if a solution conducts electricity. So here's a battery, okay, and the battery has wires coming out of it. And over here, it goes up to a light bulb, okay? And then it comes down, and then these wires kind of go into a beaker. And there's a solution in the beaker, okay? And because of the battery, you have a positive side and a negative side here on these two wires that are stuck into this solution, okay? So now what happens is this light bulb, if this is, say, distilled water in here, or if I have no solution, I take the solution away, you just have these two wires, they're not touching each other, right? So the circuit is not complete, right? There's a break in the circuit, okay? The light bulb can only go on if the circuit is complete, okay? So, so if I take sodium chloride and put it in here, what you see is a bright light from the bulb. And why is that? Well, because sodium chloride contains ions. And ions carry charge in solution. And they are actually going in the different directions, and they actually basically carry electricity. They allow electricity to flow. So this allows electricity to flow. And so the light goes on, okay? If you have instead a solution of ethanol, or just about any molecular compound like sucrose, C6H, oh, that's glucose. Yeah. How do I know, by the way, from its formula, that these have to be molecular compounds? You should be able to tell from the formula. What do you look for an ionic compound? You look for metals or ammonium. There's no metals, no ammonium. In fact, these are all nonmetals. H is not a metal. It's a non-metal. So these are all not, that's how you tell, okay? So if you put solution of ethanol in there, you would have no light. Be- No.
Like if I dump water into like. Well,
Oh, well,
or like it'll get messed up.
so you're saying, how is it that just plain water can do that and it doesn't have ions?
Yeah, like I was.
Yeah, well, I'm right. The only way you could get there to be no ions is to have super distilled water in there. Even if you put tap water in there, it would light up a little bit. Yeah, I used to have to be very careful to use some good distilled water to get it to not light up, but yeah. But anyway, so my point being, you put a soluble ionic compound, it produces ions and the light lights up. You put in a molecular compound and it doesn't. Also, if you put a solution of HCl, it'll light up like a Christmas tree. Bright light. Okay, what if you put instead acetic acid? It would light up, but it would be a dimmer light. It's because there's fewer ions. Okay, so now we have a word for these things. The fact that the fact that NaCl lights up in an apparatus like this, we say that NaCl is an electrolyte. And an electrolyte is a substance which, when you dissolve it, it conducts electricity. Conducts, that's good enough. What else is it going to conduct? I guess it could conduct heat. Okay, so that's an electrolyte. So HCl is an electrolyte. Ethanol, molecular compounds that are not acids are non-electrolytes. And then we have the distinction of a weak electrolyte versus a strong electrolyte. So NaCl is a strong electrolyte because it produces lots of ions. So we have strong electrolytes. It just wants to slow me down. Maybe that's good. It's not the pen. And then we have weak electrolyte. Conducts only a little. And then, of course, we have non-electrolytes, which do not conduct. Okay, so this acetic acid here is a weak electrolyte. And then, of course, we could also write down here for sort of completeness, insoluble ionic compounds are do not conduct. And why don't they conduct? Because there's no ions in solution there. The compound is sitting at the bottom. Okay. Okay. All right, so that's something to know about ionic compounds and molecular compounds. And I have another picture to show you. Where is it? It should be here. Here it is. So this is just another summary, and this I believe you have in your packet. Molecular compounds that are not acids, like ethanol. They have no ions, they have individual molecules, they do not conduct, they are non-electrolytes. So this is just a summary of what I really just said. Soluble ionic compounds and strong acids conduct, they're strong electrolytes. Weak acids are weak electrolytes. Okay. All right. So now we are ready for reactions. So we're going to start to talk about chemical reactions. All right. Now you think we've been talking about chemical reactions, of course, already, but I've given you all those reactions. So now we're up to the point where I'm going to give you, you're going to know how to write the products of a reaction given the reactants. So before I just gave you the whole equation, but now we're going to do some reactions that you will learn how to write the products too. So, so let's talk about reactions. Writing products of certain types of chemical reactions. Okay, so the first one is precipitation. And a precipitate, as I've told you before, a precipitation results when a reaction, well, okay, so precipitation is when you have you mix two soluble ionic compounds together. And you see a solid forms. This is what it looks like, okay? You mix these two soluble ionic compounds, so the solutions are clear, both of them. They may not be colorless, but they're definitely going to be clear. And you see cloudiness forming, and then you see a solid form. Eventually, it settles on the bottom. So when it happens is when a reaction mixture, so after you mix those together, that's the reaction mixture. When the reaction mixture contains a combination of cations and anions that correspond to an insoluble ionic compound. Okay, so this happens when the cation anion combination in the reaction mixture corresponds to an insoluble ionic compound. So you're going to have the solubility chart next to you when you do problems like this. And I'm going to show you what I mean by this, okay? So let's say you have two ionic compounds. You have lead nitrate and potassium iodide. So do we have the solubility chart? I don't know. I guess I don't. But let's take out the solubility chart. The solubility chart, I believe, is on the back of this handout that I gave out last time that I still have copies of. So if you need one, you can come and get one. So turn it over, look at the back of it. Lead nitrate. Is lead nitrate soluble or insoluble? And how do you know? How do you know? Right, because it's a nitrate. And nitrates are generally soluble with no exceptions. Potassium iodide. Soluble or insoluble? Soluble. Why? Because it's got an alkali metal ion, potassium K+. Those compounds are soluble with no exceptions. It's the first line of the compounds containing the following ions are generally soluble. So here we have two soluble ionic compounds. We mix them together. So let me write the reactants. Oh, I put aqueous, right? They're soluble, so I could put aqueous. And then I put an arrow. And now let's think about what's in the flask. Okay, so I'm going to draw a stupid little flask here. And there's water, of course. And we have lead ions. We have nitrate ions. We have potassium ions, and we have iodide ions. So now, read the top line. Precipitation. This happens when a cation-anion combination in the reaction mixture, this is the reaction mixture, okay, corresponds to an insoluble ionic compound. So is there any combination of cation and anion? Remember, cations plus, anions minus. Can we put together a plus ion and a negative ion so that you end up with something that does not dissolve in water? And what would that be? So we already, we started with lead nitrate and potassium iodide. So pairing those together aren't going to get you anywhere. Those are soluble. How about lead with iodide and potassium with nitrate? Are any of those insoluble? Exactly. So we see that if the lead comes in contact with the iodide here, there we go. So that is a combination that corresponds to an insoluble ionic compound. So what happens is you have all these ions sort of floating around in solution, and they're all encountering each other. Because of the attraction of positive and negative charges, the plus and minuses are probably encountering each other more than negative and negative, or plus and plus, because they're attracted to each other, not repelling each other. So the thing is, when a lead ion and an iodide ion come together, instead of just sort of bouncing off each other and floating around a little more, they stick. I know that because I know that lead iodide is insoluble. So there must be something that makes it insoluble. And that something is that they are attracted, these ions in a compound like that are attracted to each other more than they're attracted to the water molecules around them, because all ions attract water molecules. So I guess I would say that because this pair of ions belongs to an insoluble ionic compound, they stick. And what's going to happen is that lead iodide will precipitate. And eventually, you'll find it on the bottom. In fact, it's a beautiful, though poisonous, yellow compound that you will see sitting on the bottom. Okay. So the products are lead iodide. Now, here's another thing that you have to realize. When you put the lead with the iodide, you have to make a legal formula, right? We know how to do that. You've been trained to do this. You know that lead is 2+, and that iodide is a single negative, and that you need 2 of these to balance one of those in a formula unit, because we have practiced this. Now, it's insoluble. So we give the phase as solid, S. And the other product that we write is KNO3, but that's just aqueous. This isn't balanced yet. To balance it, I have to put a 2 here and a 2 here. So we use this technique when we do this. We had lead nitrate and potassium iodide goes to lead iodide and potassium. Oh, so what one way you can get these products, I didn't show this to you yet. Is you can do what we call double exchange or double replacement. To deduce the products, you can say and take the cation from this guy, the lead, with the iodide, and the cation here with the nitrate. So we place the cation of one with the anion of the other, and the cation of the other to the anion with the first. Okay, these are cation-anion pairs. That's the only reasonable way to do this. We found out that lead iodide is solid, and so that's the precipitate. Okay, we write the other product as the other two ions, the potassium and the nitrate. But notice, just because there was a 2 here, you wouldn't put a 2 on the nitrate here. You need 1 potassium to balance 1 nitrate. Okay, so we call this double exchange or double replacement. You'll see this a lot. Cation of one with the anion of the other. And we do that twice. Okay. So let's see. So I want you to understand, though, that this isn't, it makes it sound like these things are doing a dance and they're switching partners and things like that. And that's not really what's going on here. What's going on is we have these ions that are floating around in solution. And like I said, when the plus ion, minus ions belong to an insoluble ionic compound, they stick together. But I got to ask you, what do you think is happening with the K plus and the NO3 minus ions? Do they stick together? No, because they do not belong to an insoluble ionic compound. The K plus and the NO3 minus ions are still just floating in solution. In fact, that aqueous there means that they really exist as K plus and NO3 minus. So they're sort of just there. They're like sitting in the stand watching the reaction. Yeah. That's just a way of writing it, honestly, because it's maybe easier to write it than separating the ions. But you can do the following, all right? So let me balance this. I did it already, but I'll do it again. And I think I need a 2 here. Okay. So I would say that these are still floating around in solution. They did not do anything. They didn't participate. So we call these spectator ions. That's what K plus and NO3 minus are. They're spectator ions. And so what we can do is we can write this equation in a different way. Okay, so I could write all the aqueous compounds as ions. So I can write Pb2 plus aqueous plus 2 NO3 minus. Like all the aqueous compounds, I can just write them as the ions that they are. Okay, plus 2K plus aqueous plus 2 iodide aqueous. Doesn't look any easier, does it? Because notice I have to realize that the 2 goes with both of those, right? And it goes to, all right, now, can I break PbI2 into ions? No, it's not even in solution. It's sitting on the bottom, right? This is the precipitate on the bottom. So I can't break that up into ions because it doesn't exist as ions in solution. I can't do that. So I can break this up because it's aqueous. And now I could do something else. I can get rid of these spectator ions by canceling them out. So let's see, I have 2 nitrates and 2 nitrates, and 2 potassiums and 2 potassiums. And now you could see essentially what is really going on in this reaction. And that is that the lead, the aqueous lead ions, finds the aqueous iodide ions and forms the lead iodide precipitate. This is called the net ionic equation. I used to spend a lot of time teaching net ionic equations in this course, but in this year, I'm making it an extra credit topic. Okay, so there's a handout in this packet. Let's see. It's like the 5th or 6th page in, and it says writing net ionic equations. So this gives you detailed instructions on how to write net ionic equations. But like I said, it's extra credit in fall of 2023. So if you're interested and you like this sort of thing, you can read this in detail. And on the bottom, there's a special problem where you could go to activity 6, and for several of the equations, you can write the net ionic equation. And there's a funny B at the end of that sentence that's probably doesn't belong there. So you can just cross that out. But anyway, just go to the net ionic equation. So this is, like I said, net ionic equation is an extra credit topic this term. It says 2. All right. So let's go over what you have to do again to write, to do a precipitation reaction. So precipitation. Which basically means you don't have to know how to do what I just did. So first, you can do double exchange. Right? And you're looking for an insoluble combination of plus and minus ions. Okay, the second thing you want to do is you have to make sure you must write the correct formulas. And what I mean by that is if we go in back and look at the equation here, you know, remember we don't have what's on the right at first. If you were to say, okay, I have 2 nitrates here, so my nitrate on this side must have 2 of them in the formula. No, the formulas are the formulas, and we know how to write correct formulas based on the ions. So don't let the fact that you need 2 nitrates on the right have you put a formula with 2 nitrates. You need to figure out, you need to balance the equation to get those numbers right. But you must use the correct formulas like you've been trained to do since chapter 2. Okay. So 3, once you have the products, see if one is insoluble. And that will be the solid. So you'll put S. Okay. The others will be aqueous. Okay, and then finally you'll balance. So let's go ahead to chapter 6, activity 6 from chapter 4. Let's see, here it is. So here's the first one. K2S plus FeNO3 2. So you're going to start by doing double exchange. So you would end up with a compound that has, so let's look at the formulas here. We would have K plus and NO3 minus. So what's the formula of that going to be? You'd have one of each, right? We did this already. This is the same as the one we just did. So this would give you KNO3, right? And then you have Fe. Now Fe is 2 plus here because there are 2 nitrates, right? So we know it's the iron 2. And sulfide. What's the charge on a sulfide? 2 minus. So what is that going to be? Yeah. So that's going to be FeS. And now you look on your chart in the back here. Tell me, which one of those is insoluble? The sulfur one, yeah. So that's going to be solid. KNO3, that's a nitrate, aqueous. This started out as aqueous, and potassium sulfide, right, is going to be what? It's potassium. Potassium is an alkali metal. When they're paired with just about anything, they're soluble. That's what the chart tells you. So here we have our reaction. This is our precipitate. Okay. And so it just remains to balance it now. So what do I have to do to balance it? That's it. Okay. So that's the first one. Okay, why don't I'll do the third one because strontium is not something we see a lot. So where is strontium in the periodic table? Yeah, I wish I had one in the room, but I don't. Say that?
2 plus.
Yes, it's in the second group 2A or 2. So strontium is 2 plus. So when I do my double exchange here, give me one product.
That's
Well,
fine. Wait, no, sorry,
you can't pair two SR SO4. Right, because I have one strontium 2 plus, one SO4 2 minus. Okay, by the way, let's first figure out the phases here. All chlorides. Wait a minute, what is, actually, I don't remember that. Yeah, strontium is not an exception to the chlorides are soluble rule. So that's aqueous. Anything with sodium is aqueous. So we have SrSO4, and the other product is NaCl. Don't be fooled by the 2 here and the 2 here. Do not write Na2Cl2. The formula is NaCl, right? So you work it out in the balancing when you need to change the numbers of each. And we know that sodium chloride is soluble. So here's the products here. Yes, because sulfates are generally soluble It's the last rule of the generally soluble, last line, but strontium is an exception. And so it's insoluble. So we have this equation here, and how do I balance it now? Right, and yeah, looking at the wrong one, yeah. All right, so why don't you folks do 2 and 4? Have you got any questions? All right, so number two, we have lead with chloride. That's Pb2 plus. You know it's 2 plus because it's with two nitrates here. And we have Cl minus. So when you put that together, you'll have oh well, it wins. Oh, now I have to erase. All right, whatever. Can't make a mistake. And you would look that up, you'd find out that chlorides are generally soluble, but when paired with lead, they're not soluble. And the other one is NaNO3, which is aqueous because it's a nitrate and it has sodium. So those are the two products. You need to have two nitrates. So now you need two of these, so that's balanced.
If you know you're doing this type of problem, figure out that one of the products is aqueous.
No. No, you don't really know. He's asking if you know, if you put these together, you see one, you know, sodium nitrate is soluble. So, oh, it must be that PbCl2 isn't. Well, in this case, that's true, but I'm going to show you an example later where that's not true.
So is it not?
Well, okay, so suppose you mix two soluble compounds together and you don't get a precipitate. You don't always get a precipitate because there might be combinations where cation anion pairs are all aqueous. That's essentially no reaction because nothing has really happened. You had ions in solution at the beginning and you have ions in solution at the end. I'm going to give you an example like that. I think it's number 13, but I'm not sure. It's like gray at the end. All right, let's do this one. So we have lead with bromide and aluminum with nitrate. Al. Okay, what is this going to be? All right, so Al, you could see it's 3 plus here because it's with 3 bromides, which are each 1 minus. So now it's going to be with nitrate. So it's going to need to be with 3 of them. So that's the formula. It's a nitrate, so it's aqueous. The other one is Pb with bromide. Because we know that lead is 2 plus and bromide is a single negative. So that's the ions that you'll have in one formula unit.
Isn't it 2 NO3? I don't.
2 NO3. It's 2 on this side. You see, you can't use that to make a judgment about what that formula is. You have to use the ions to make a judgment about what that formula is. The 2 will come into play later when we have to balance the equation. But it's essential. This is a mistake that students make all the time. Do not base your formulas on the right on the subscripts that are used on the left, right? The subscripts on the left are because of the particular anion-cation combination and that you need a neutral compound. Yeah. No. No. Okay, bromides are generally soluble, but not when paired with lead from the solubility chart. So this one now, all that remains is for it to be balanced. This is a little tough to balance. You see you have 3 BRs here, you have 2 here. So usually that means that you would have to put a 3 here and a 2 here. And that would mean you'd have to put 2 here for 2 aluminums, but that means you'd have 6 nitrates. So you have 2 here, so you'd put a 3 here, and lo and behold, that works because you had 3 PBs. If you do not have the right formulas, lots of times you could try balancing this thing forever, and you're going to pull your hair out. Make sure you have the right formulas based on the charges of the ions in that particular compound. Okay, I can't stress that enough. Okay, enough with precipitation. Let's move on. Yeah, that's right. There's 3 times 2 here as well. Yeah, it works. Okay, so I want to talk about some reactions of acids and bases. Well, actually reactions of acids and not. Okay, and the first one is one that we're somewhat familiar with from earlier in the term. Oh, first I want to tell you, just review that we know about acids. I've just talked about them. But what about bases? You remember what I told you earlier, that bases produce OH minus in solution. So for our purposes in this course, metal hydroxides are bases. Okay, so a lot of times you'll see a metal hydroxide, and of course they'll be soluble if when you look on the solubility chart, a lot of hydroxides aren't soluble, but a lot of them also are. Okay, so that will allow you to put a solid or an aqueous. Okay, so can be, oh, I'm not going to write that. All right, so what is the first reaction I would like to talk about is an acid base neutralization. Maybe I did not plug this in. Remember, that happened last time. And that is indeed the case here. All class, I've been struggling because my thing is running out of power. Let's hope it gets better now. I plugged in this side, but not this side. All right, acid-base neutralization reactions. Okay, so here's an acid, nitric acid. It's one of the 6 strong acids. Okay, and acids are aqueous, right? They dissolve. And KOH, this is a metal hydroxide. If you look on the solubility chart, because this is an ionic compound, you see that it's soluble. So it's aqueous. So in an acid-base neutralization reaction, the fundamental thing that's happening is the H plus from the acid combines with the OH minus from the base. And what does it give you? Water. So H2O is always a product. What's the other, and by the way, H2O is liquid, okay? What's the other product? Well, you look at the other remaining ions, all right? So you know when you put this in water, it's going to break into H plus and NO3 minus. So nitrate ion is up for grabs. And here we have K plus and OH minus. So the K plus is up for grabs. The OH has already been incorporated with H plus into the water. And so you end up with KNO3, which is aqueous. So the H plus from the acid combines with the OH minus from the base to produce water. And the other product comes from the leftover ions. Here we have K plus and NO3 minus. They form a salt. This is called a salt. It's not sodium chloride, but it's another salt. There's many, many salts. So the products of an acid-base neutralization reaction are water and a salt. And by definition, what a salt is it's an ionic compound that's produced from an acid-base neutralization reaction. So that's what chemists call a salt. So a salt, I know, is an ionic compound produced from an acid-base neutralization reaction. So for example, if you had HCl, that's an acid, and sodium hydroxide, a very common combination, a base, you get water and our favorite salt, NaCl. That's why it has the name salt, okay? All right, I don't know if I balanced the one up there. Yeah. Okay. So when you try to find the products of an acid-base neutralization, you can think of it as a double exchange. In other words, you could put this H with this OH minus to get HOH, but you have to write it as H2O because that's what it is. And then you have this anion with this cation to give you the NaCl. So you can think about it as a double exchange. You can use the so-called double exchange for acid-base neutralizations. I prefer just writing water and then figuring out what the other ions are, but it works just as well. So if we do, let's do reaction number 6 first. Okay, number 6. So you could say take the H's from here and the OH from here, and then write, so you know that the first product is water. Well, it doesn't have to be first. You could write it second if you want. And the other product is going to be from sodium and sulfate. So what's the formula going to be? Right. Because you need 2 to balance 1. And sodium sulfate is aqueous. So these are the products of this reaction. But this does need a little balancing. So you could see that you have 2 H's here. So you would need to combine with 2 OH's to get 2 waters. And that's right, that's perfect because you have a Na2 there. So like I said, if you get the formulas right, the balancing is much easier. You can't really balance a lot of the time if the formulas are wrong. I didn't put the phases here. But again, you have to use your solubility chart, except this is an acid. Acids are soluble. Okay. And sodium hydroxide is a soluble hydroxide because it has sodium, and sodium is an alkali metal, and it's always produces soluble ionic compounds. So there's that equation. What about this one? What's the one product going to be? H2O. And what are the leftover ions? Right, we have magnesium and chloride. We would need 2 of these to balance 1 of those. All right, now we have to figure out the phases. So what is the phase of magnesium hydroxide? So hydroxides are generally insoluble. It's in the second group of compounds. But when hydroxide pairs with calcium, with magnesium, oh, no, it's no exception. So this is actually solid. Okay, it's not an exception. You see what I'm talking about? Look at your solubility chart. Hydroxides are generally insoluble, right? And magnesium is not an exception. So it's, yeah, so it's solid. God. It is a little confusing that S is solid, but S you think would be soluble, but aqueous is soluble. It's just life in the chemistry city. And the chlorides are soluble. Magnesium is not an exception. So now it just remains to balance. And you could see you have 2 hydroxides here. So each one is going to need an H to combine with. So you're going to need a 2 here. So you get 2 waters when you do that. Or you could just balance based on the numbers of each. But it really is easier to see that if you have 2 hydroxides, you're going to need 2 H's here. So you're going to have to put a 2. And indeed, you have a Cl2. So that would tell you also that you needed 2. So this is the equation. Would you like to do number 8? All right, now 8 is a weak acid. But it's the same strategy. So just you guys do that one. So what's one product? And what are the leftover ions? Well, okay, so look, we have H, C2, H3, O2. So when we get rid of the H plus, what remains is C2, H3, O2 minus the acetate ion. Okay, so we have lithium and we have acetate. And when we combine them together, we have a 1 plus and a 1 minus, so it's a 1-to-1. We have LiC2H3O2. Aqueous. Because acetates are always soluble. So acids are soluble. Lithium hydroxide, it's an alkali metal, first column in the periodic table with a hydroxide, so it's soluble even though it's a hydroxide. And balancing this, you have one OH and one H to give you one water. Nothing else is necessary. Yeah. No, that's actually not true in this case. When you put it in water, not much dissolves, but when you put it with a base, that base is taking that H plus. So it's stealing all of them. Yeah. Yeah, it's already balanced. That's right. Okay. All right. So now I'd like to tell you about another reaction of acids, which a couple of different reactions. We have acid plus carbonates. Okay, and carbonates are like sodium carbonate, which is aqueous, you know, it's soluble, I guess I should say. And magnesium carbonate, which is insoluble. Okay. And then there's also acid plus bicarbonates. Does anybody remember what the bicarbonate ion is? HCO3 minus. So for example, sodium bicarbonate is what you have in your kitchen shelf or, you know, cabinets. That's sodium, what is it called? Baking soda, right? Which you could have calcium bicarbonate. Oh, and another thing is I don't have it on the solubility chart, but you should write it in. You should put where it says nitrate and acetate. So it's like the second one down here. Add bicarbonate, HCO3 minus. Bicarbonates are soluble, okay? So put that in on the solubility chart somewhere. I would put it next to where it says compounds are generally soluble, go down where it says nitrate and C2H3O2 minus and HCO3 minus. HCO3 minus bicarbonate compounds are generally soluble with no exceptions that I think. Okay.
There.
What?
It is there.
HCO3 minus?
Yeah.
Where? Really?
No.
No, it's not. Do you have a different chart? That's acetate. Maybe you print. Maybe I rewrote it sometime and put it in. I don't know. Show it to me after. Okay. So what happens? Let's start with, well, so acid plus carbonate or bicarbonate. gives you a salt plus carbon dioxide plus water. So I'm going to go over this with you and show you the steps that happen to get to this product. There's just 2 steps. It doesn't want to move. Okay, there we go. Okay, so I'm actually going to use this as an example here, this lithium carbonate plus H2SO4. So this is a carbonate. And this is sulfuric acid. Okay, and you can use the double replacement method, the lithium from the carbonate here with the sulfate and the H's with the carbonate. Okay, so the first one I want to go over is the one with the arrows on top. H2CO3 is one of the weak acids on the weak acid chart. This is called carbonic acid, and you should know this name. You should know acetic acid and you should know carbonic acid. H2CO3 is always a product here, but it is not the final product. So let's first write the sort of the first step. You'd have the H's from here combining with the carbonate. And you know that H is an H plus ion. So you need to have 2 H pluses with 1 CO3, 2 minus, except that H2CO3 is not an ionic compound. It's a molecular compound. It's a weak acid. Okay. So that, the other product is a salt, which is from the leftover ions, the lithium and the sulfate. But that's not the right formula because you need 2 lithiums to go with 1 sulfate. So it's Li2SO4. That is not the final product because this guy, H2CO3, is not stable. It's unstable. And what happens is that it breaks down into 1 carbon dioxide and 1 H2O. So it forms immediately H2O and CO2. And you'll notice that it adds up, right? You have 2 H's, 1 O from the H2O, 2 O's from the CO2, that makes 3 O's and a carbon. So the H2CO3 ends up forming liquid water and carbon dioxide. So the final products are H2O plus CO2 plus lithium sulfate. So to write the whole thing again, lithium carbonate, which we never put in the phases, so we have to do that now. Okay, H2SO4 is an acid, so is it soluble or insoluble?
Yes.
Soluble, yep. Lithium carbonate is a carbonate. Carbonates are generally insoluble, but not when paired with lithium. Lithium is in the first group of the periodic table. If you look on the solubility chart, carbonates are generally insoluble, but when they're paired with lithium, sodium, etc., they're soluble. So this is aqueous. Oh, I wrote an S here. Yeah, sorry.
Carbonic acid, not stable.
It's unstable. It's just, it's not a stable structure.
This one is liquid and the other one's gas, so.
No. No, nothing to do with that. It's probably just that carbon dioxide and water are much more, have much stronger bonds than H2CO3. Okay, so, all right, so is this balanced? So here's a clue, here's a trick for you. What I do is I always balance it by looking at this version of the equation. I always balance it before it breaks up to H2O and CO2. here you could see that there's two H's here, there's two H's here, there's CO3, there's CO3, there's two lithiums, this is balanced. And whenever you have one H2CO3, you'll have one H2O and one CO2. If you had two H2CO3s, you'd have two H2Os and two CO2s. So it's just an easier way to balance. But anyway, this equation is balanced. So let's just do, let me show you an example of acid plus bicarbonate. It's the same idea. You get carbonic acid, and then the other ions combine to give you a salt. And that carbonic acid, again, is not stable. So this is, say, number 11. I don't know if I have number 11 here. Oh, look at that, number 11, right down there. Okay, so in the first product I'm going to write is H2CO3. Okay, but I know that that's not the final product. And that's because you see I have an HCO3 minus here combining with an H plus from the acid. And notice there's two H's and a CO3 and the charges cancel. And this is a molecular compound. It's a weak acid, but it is not stable. This computer's driving me nuts today. Nuts. Yeah, it isn't. That's true. Oh, stupid little thing going round and round. Love ya. Okay, and then the other ions, what is the other product here? Yeah, magnesium bromide, which is, what's the formula for it? Is that right? No, Mg is 2 plus. Yeah. Which is it aqueous? Yes, it is. And now, okay, and we know the acid is aqueous, and we know bicarbonates are, we just wrote it in that they are all soluble, so this is aqueous. So we have as a final answer, well, without balancing, I haven't looked at that yet. H2O. Actually, let's look at this. Let's balance it first. We need to put a 2 here, right? Because you have each HCO3 minus needs an H plus, and there's 2 of them. So we'd have to put a 2 there. Also, there's Br2. So there's 2 reasons to put a 2 there. So we will end up with 2 H2CO3s. And 1 MgBr2. So because I have 2 H2CO3s, that tells me that I'm going to need 2 waters and 2 CO2s. This is liquid and gas. And MgBr2 aqueous. So that should be the final answer. All right. So how about you work on these 3? And I'm not telling you which is which. You have to figure it out. These are different types of reactions that we've studied today. And also, I'd like you to look at 13. 13 is one that's that exception I was telling you about earlier. 7, 10, 12, and maybe 13. I don't think you have enough time to really finish all that, but you can start. I'll come around.
Is that something you put out there at the end of the day, or is that just? Oh, there's like 15 reactions of it. That's what you get. Have to worry about the balance later. You always get carbonic acid. There's no such thing as any steel free water. So that's 100% safe. That's balance. I like it. Lots of blood. Yeah, given that this is a field right now, we're just gonna take one option. Yeah. Class is basically over. You can look at them later. Maybe I'll go over them next time.
All right, I gotta stop